So now that we have a good understanding of what it means to be an acid and a base, we can start doing math. So lesson 2 is going to be all about your strong acids and bases. Lesson 3 will be your weak acids and bases. So the first thing we're going to start with here is the equilibrium constant for the ionization of water. Think about that word, equilibrium constant. That's going to bring up that letter K. And now, instead of KEQ or KSP, we're going to be talking about something called KW, which is the ionization of water. So the self-ionization of water is that even pure water contains very small amounts of ions due to collisions between water molecules. So two water molecules can collide with a bit of heat, making it an endothermic reaction, producing hydronium ions and hydroxide ions. If I said that this was at equilibrium, I can write the equilibrium constant as hydronium divided or times hydroxide divided by water squared. But we have to be careful. Since water is a pure liquid, its concentration is constant at a given temperature. Therefore, the hydrogen would get, or the water would get incorporated into your constant, and we wouldn't include it as part of our KEQ. This is our equilibrium expression for the ionization of water, and we're actually going to give it a new name, which is the equilibrium constant for water, or the ion product constant for water. And we call it Kw. And Kw is the concentration of hydronium times the concentration of hydroxide. And the nice thing is that at 25 degrees Celsius, the Kw is always 1.00 times 10 to the negative 14. This is a value that we'll be using a lot, and it's right now not in your formula sheets, but I think I will add it into your formula sheets. So it's something that I would definitely write down. So the Kw, or the ionization constant, or the product of hydronium and hydroxide in water at 25 degrees Celsius is always 1.00 times 10 to the negative 14. And there are no units on equilibrium constants. Now let's talk about this 25 degrees Celsius for a minute. What do we know about temperature? Well, we know temperature changes everything, right? Think about unit 3. Temperature would change the solubility of a product. I was trying to, like, what's the word? A solubility of a substance. There we go. It changes the solubility of a substance. So when we did our tables, it was always at a certain temperature because otherwise the KSP changes. Well, Kw is no different. This is the value of Kw at 25 degrees Celsius. How would temperature affect Kw? Well, think about the fact that this is an endothermic reaction, right? Heat is a reactant. If you were to increase the temperature of a system, then what would happen? Well, the equilibrium would shift right and the products would be favored, which means the concentration of hydronium and hydroxide would increase, which would cause the value of Kw also to increase. Whereas if temperature was decreased, equilibrium would shift left to produce more heat and the reactants would be favored, which would mean the concentrations of hydronium and hydroxide would decrease, and that would actually decrease the value of Kw. So temperature has an effect on this ionization constant for water. The flip side of this is, well, what if we were to use something like the common ion effect? What if I added an acid? Well, if I was to add an acid, it would release hydrogen ions, right? They donate hydrogen or donate a proton, and they would do that to water. So the concentration of hydronium would increase. If you look at your reaction, right, hydronium is a product. If I was to increase the concentration of hydronium, my equilibrium would shift left. And when you shift left, that's going to require more hydroxide to form with the hydronium or to accept the proton. And so the concentration of hydronium would decrease. So the Kw is going to remain constant because you have this increase and decrease until you get back to 1.00 times 10 to the negative 14. Whereas with a temperature change, they both increased, which meant the entire Kw changed. So same thing if we added a base. If you add a base, the concentration of hydroxide would increase. So equilibrium would shift left, also decreasing the concentration of um, the hydronium, which means your Kw will remain constant. So the key thing here, you don't have to worry, like we aren't going to do a lot of Le Chatelier in this unit, but the key thing to know is that the only thing that's going to affect the value of Kw is temperature. Okay, so now that we've got that out of the way, let's start doing some Kw calculations. So using Kw in calculations, the questions will say something like, what is the hydroxide ion concentration in a sample of 0.025 molar hydrochloric acid at 25 degrees Celsius? So the first thing you're going to recognize is that this is a question involving a strong acid. Why does that matter? Well, it matters because hydrochloric acid will completely dissociate into its ions. So hydrochloric acid with water, one-way arrow, forms hydronium ions and chloride ions. So if we know that the concentration of hydrochloric acid is 0.025 molar, we know this is going to be in a 1-to-1 ratio with the hydronium. So it is going to produce 0.025 molar hydronium ions. And acids, strong acids, will always be in a 1-to-1 ratio with the hydronium they produce because you can only donate one proton at a time. So whatever the concentration of the acid is also the concentration of your hydronium ion. So we know that the concentration of hydronium is 0.025 moles per liter. So now what we're going to do is we're going to use this value of Kw, Kw being the ionization constant of water, equal to the concentration of hydronium and hydroxide ions in solution. So for this, we're going to put in that Kw is 1.00 times 10 to the negative 14. We can put in that the hydronium concentration is 0.025, and we can solve for hydroxide. In other words, we can take this equation and rearrange it to say that the concentration of hydroxide will equal the ionization constant of water divided by the concentration of hydronium ions in solution. So we're going to do the 1.00 times 10 to the negative 14 divided by the 0.025, and then we would get 4.0 times 10 to the negative 13 moles per liter of hydroxide would be present. So the key thing with this is that when you are at 25 degrees Celsius, the equilibrium constant of water has to be, like it says, constant. So if the concentration of hydronium is 0.025, there is still hydroxide, and it would be 4.0 times 10 to the negative 3. Okay, three more questions down here. We are going to determine the hydronium and hydroxide ion concentrations for the following. So let's start with this guy, another strong acid. If the concentration of the acid is 0.0010, then the concentration of the hydronium ions is also 0.0010. If we wanted to find the concentration of hydroxide, we would do Kw divided by the concentration of hydronium. Now, I'm choosing, because we do this calculation a lot, to rearrange it and write it in the rearranged form. If you want to do like I did above, where I wrote it as Kw equals the product of the two ions and then rearrange, that's totally fine. So I'm just going to put in 1.00 times 10 to the negative 14 divided by the 0.0010. And then if I plug that into my calculator, first time we've touched a calculator in a while. 1 times 10 to the negative 14 divided by 0.001 is, now keep your sig figs, this is 2 sig figs, so 1.0 times 10 to the negative 11. And since we're solving for a concentration, it would be moles per liter or molar. Now what we're going to do is we're going to switch to a strong base. Now for the strong base, we know that barium hydroxide will dissociate to barium and two hydroxides. So if the concentration of barium hydroxide is 0.0300 molar, then the concentration of hydroxide is going to be twice that. So the concentration of hydroxide will be 0.600 molar. Then if I wanted to find the concentration of hydrogen, again, we know that Kw equals hydroxide times hydronium. So the hydronium is going to equal Kw divided by hydroxide, which gives me 1.00 times 10 to the negative 14 divided by the 0.600. Now this time, we're going to answer with 2 sig figs. So 1 times 10 to the negative 14 divided by 0.6 gives me to 3 sig figs 1.67 times 10 to the negative 14. Oops, 14 moles per liter, or molar. Awesome. Okay. Now you'll notice with both these species, this was an acid, so there was a lot more hydronium ions than hydroxide. This one was a base. There's a lot more hydroxide than there is hydronium. Last one I threw in just because it's pure neutral water, and we haven't really talked about this yet. They didn't give us any values, but we know that if something is neutral, then the concentrations must be equal. So the fact that something's acidic is the fact that more hydronium ions are present in solution. If something's basic, there's more hydroxide. So if something is neutral, then these two values have to be the same. So what we're going to do is say that the Kw of water is still 1 times 10 to the negative 14, but both of these concentrations will be the same. Let's call them X. So if I wanted to know the concentration of either of those ions in a neutral solution, I'm going to take the square root of the Kw. And I will get that X is equal to 1 times 10 to the negative 14. And I'm going to take the square root of that. Oops, I had to do that first. Square root of 1 times 10 to the negative 14, which gives me 1.00, maintaining sig figs, times 10 to the negative 7 molar. So the concentration of hydronium will equal the concentration of hydroxide, which will equal X, which is each 1.00 times 10 to the negative 7. Awesome. Okay, go practice those calculations.